This is Algebra 2 at Trig. We're working on Unit 4.1. These are relationships between functions and their inverse. So the first thing we're going to notice here is that we have a table. And if you take this table and plot it out, it would make a straight line in this case. This is the inverse of this table. Notice where the points are. Notice what happens when you switch the X and the Y. We are creating what's called an inverse. We have another table here. We have two tables. They are inverses of each other. So if you take the Y values of the original, they will become the X values of the inverse. And the X values of the original will become the Y values of the inverse. So if you notice, the range of the original is going to become the domain of the inverse. And the domain of the original is going to become the range of the inverse. So what do we notice? The X values and Y values switched between the original and inverse. We'll call it a relation. Rather than a function, we'll call it a relation. Because the inverse might not be a function. So an inverse relation is a reflection of the original relation. So that means we're going to take all of our X values, -3, -1, 0, 2, and 7, and turn those into our inverse table. So we're going to bring those down to our Y values. And then our Y values of the original are going to become the X values of the inverse. Those are called inverses of each other. So now you simply know how to make a table from the original to the inverse. So here we play with it again. The X values become the Y values. And the Y values become the X values. And voila, we did it. We made the inverse table if we know what the original table is. If we're given a domain of the original graph, we can determine what the range is. The X values become Y values. So if your domain, which are X values, is going to become the new Y values, then the domain is going to become the range. And if your y values are going to become the new x values, then your range is going to become the domain. Same idea here. Your domain of the original, those are your x values. So your domain is going to become your range because your x values become your y values. And your range is going to become the domain. The y values of the original are going to become the x values of the inverse. It seems simple enough, but can you follow what that's representing? Let's take a look and see what graphs look like with this. How are graphs of an inverse relation related? Well, we're going to take our original graph, 3x minus 1. We know how to graph by going down to -1 and then doing a slope of 3. That's rising up 3 and going over 1, rising up 3 and going over 1. So that's where this graph has been created. Down 3, backwards 1, down 3, backwards 1. So there is your equation. We would call this f of x, and that is 3x minus 1. So now if we're going to graph the inverse, what we would do we would graph f prime of x, that is f inverse. We put a little apostrophe, a little mark up above the f to show that this is the inverse, kind of like prime when we talked about in geometry. So what used to be the function or the y values is now going to become the x values. And what used to be the x values are now going to become the y values, or in this case, f of x, f prime of x. So there's your new table. So plotting that new table can be pretty simple. 1, 2, 3, 4, 5, 6, 7, down 2. 1, 2, 3, 4, down 1. Over 2, up 1. Over 5, up 2. And there is our new graph. There's our inverse. We call that f prime of x. F inverse is what the terminology would be, f inverse. We don't know what the equation is yet. You could probably figure it out. if you can notice where it crosses the y-intercept, be a little tricky here, but you know what the slope is, and you could probably figure out some different values like that, but we're not writing inverse today. So let's go ahead and talk about this one. Notice if we zoom in closely, this graph is touching at 0, -4, 1, -3, -1, -3, 2, 0, -2, 0. Now we know that the original equation is x squared. So we're just taking the parent function of a parabola and dropping it down 4. So we've gone over 1 and up 1. We've gone over 2 and up 4. So we're going to go over 3 and up 5, 6, 7, 8, 9. And that's right on the graph. One way that we can figure out where these new points are going to go is to actually reflect it across this line. If we go diagonally, if we go one diagonal to get to your line of reflection, we're going to go one dot past it, one diagonal past that line of reflection. Here we're going the other direction. We're 1 away from it. So we're going to go 1 away from it on that side. 1, 2, 3. So we go 1, 2, 3. Let me try that one again. I may have counted wrong. Sorry. 1, 2. So we go 1, 2. That seems better. This one's going to be 1, 2. So we go 1, 2. This one's 1. So we go 1 past it. This is 1. So we go 1 past it. And this one, the final one. 1, 2, 3, 4. So we go 1, 2, 3, 4. And if we connect those dots, we used to have a parabola that opened upwards. We now have a parabola that opens sideways. How did we plot those dots? We counted our diagonals to the line of reflection and went past it. Your line of reflection for an inverse is always y equals x. So it's always easy to find. You're switching your x's and y's. So that's why the line of reflection is y is the same thing as x, y equals x. Of course, some of you might prefer to use x and f prime of x. Take all of your y values and make them your x value. Take all your x values and make them your y value. They would still be all in the same spot. 0, -2, -3, 1, -4, 0, -3, +1, 0, 2. They would all still be on our inverse. The dotted line on the graph is y equals x. What do we notice about the graphs of the inverse relation and the original function in regards to that. It is a reflection over the line y equals x. What do we notice about the graphs? A reflection over y equals x. So the graph of a function's inverse is the reflection of the original over y equals x. So if we know how the inverse function is made, we can come down here and graph them out. You're welcome to make a table, but that sounds like more work. I'm just going to plot it out. Then I'm going to reflect it over the line y equals x. I'll zoom in nice and close for you. So we're going to start up at 6. 1, 2, 3, 4, 5, 6. Then we're going to do our slope of rise over run. Rise up 2, run 3. Up 2, 1, 2, 3 over. Y over x. Then we're going to go down to -3. That would give you the same slope. Down to -3. Down to -3. So there's our graph. And this would be f of x equals 2/3 x plus 6. You want to label your graph. Now, for us to graph the inverse, we have to reflect it over the line y equals x. So that's our line y equals x. It has a slope of 1. It goes through 0, 0, up 1 over 1, up 1 over 1. It goes right through that line. So if we want to graph the inverse, we're going to count our diagonals. 1, 2.5. So we're going to go 1/2, 1, 2. 1, 2, 3, and 1, 2, 3. 1, 2, 3.5, 1/2, 1, 2, 3. 4. There's our 4. So that is our f prime of x. You could have figured out those points and then switched them over. We know that we have, let's see, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. So 3, 8. 0, 6, 1, 2, 3, 1, 2, 3, 4, negative 3, 4, 1, 2, 3, 4, 5, 6, negative 6, 2. So that would have been the table of the original. So then clearly we could have made a table of the inverse. This would have been 8, 3, and 6, 0, 4, negative 3, and 2, negative 6. We can test those out to see if it worked. 1, 2, 3, 4, 5, 6. There's our 6, 0. 7, 8, 1, 2, 3. So 8, 3 worked. 1, 2, 3, 4, 1, 2, 3. And 2 to the right and 6 down. Perfect. So there's two different ways you can graph the inverse. You can either reflect it over the line y equals x and actually count your diagonal, or you can make the table and switch the x and the y. We'll try this one. Well, I know this is a parabola. This is x squared. It's been stretched vertically and it's translated down. It's not translated right or left any. So there is 8 down. Now a parent function would be 1 over 1 up, both directions. 2 over 4 up, both directions. 3 over 9 up, both of directions. So that's what the parent function would look like. But this isn't a parent function. This is twice. This is vertically stretched by 2. So instead of going up 1, we're going to go up 2. Instead of going up 4, we're going to go up 8. And instead of going up 9, we're going to go up 9 extra, or up 18 total. So that's how we can graph a parabola. You need some understanding of how it relates to your parent function. So this is f of x, and that's 2x squared minus 8. So then we can look at our y equals x. So now we want to take our points and reflect over that line. One to get to the line, 1 to get past it. 1, 2, 3 and a half, 1, 2, 3. 1, 2 and a half, 1, 2. 1, 2, 3, 4, 1, 2, 3, 4. And that is our f prime of x, or called our f inverse. We don't know what the equation is. We haven't talked about that. You can see that your domain, by the way, your domain is all real numbers. It goes right and left. Slowly but surely, this is going to keep moving to the right for the original function. And the range are all your y value, your range. Yep, that's going to be all real numbers also. Your range, sorry. It's from negative, it's your y values greater than or equal to 8. And that would actually be a negative 8 because it's down here. It's going up. All right, for your blue graph, the domain I did that backwards. Silly, I didn't even think. I just was doing. Okay, let's take a look at the blue. The range, that's your y values. The y values keep getting higher. The y values keep getting lower. So that would be all real numbers. But the domain, the x values, is x is greater than or equal to negative 8. Your x values go all the way back to negative 8, but then they move to the right forever. So it's greater than negative 8. That would be your domain and the range of those two. All right, everyone. There you have it, some inverse relations.